Okay, couple things. Let's review something. Really cool trick. Probably showed this to you. Well, actually, a lot of you guys haven't had it before, so I haven't showed this to you. Maybe you've seen it. Some of you in geometry last year, we might have covered this, but I don't know that we would have. Okay, what do you do in situations like this? Let's say we've got something like 2/3 x minus 1/4 equals 2/5 x plus 5/7. Do I really want to make that a 7? It's probably not. Let me make it. Oh boy, that's going to be kind of ugly. Make it a 6. Okay, so yeah, something like that. Now, fractions are just numbers, and they're just inconvenient to work with lots of times. The arithmetic of fractions is a little bit more difficult than the arithmetic of integers, but we just deal with them the same as normal. Now, if we weren't going to, well, how could we do this problem? What are the steps we'd have to do to solve for x here? Say it again. Okay, yeah, I mean, we're going to have to get some common denominators for sure, but let's not worry about all the mundane stuff like that. Just broadly speaking, what do we do in a situation like this if we want to solve for x?
Combine like 2.
Go ahead. Did you say it again, Julia? Okay, yeah, we're gonna combine like terms, aren't we? Right? This is the same kind of problem. Now, if instead of having all these fractions, what if, I'm just going to, real quick, I'll make up another one just to kind of review what the process is, and then we'll come back to this harder one. What if I had something like 3x plus 2 equals x minus 5, something like that. Now, in general, if I want to solve for x here, what do I have to do first? Combine like terms. Good. And there's a good reason for that. Here's a statement that you'll use it a ton. You can file this away in your brain. When we're trying to solve for x, we're trying to isolate x, right? But I can't isolate x unless I have a single x up there. How many x's do you see? 2. There are 2 terms with x's in them, and so we can't isolate x unless we first simplify things. We got to compress everything down to a single x, and then we can isolate, right? This is a very simple problem, and so we don't need to probably invoke the order of operations tree, but I'm just going to point something out to you. When we're trying to isolate x, remember that we're working backwards through order of operations. Isolate or solve, we'll go in that direction. But if there's not a single x to begin with, we have to start off simplifying. We got to go down the order of operations tree to simplify first. Once we get to the point where everything's simplified and I've got a single x, then I'll turn around and I'll go back up the order of operations tree. Okay? So in this case, it's such a simple, there's so few steps and they're so simple that we don't really have to think about it that way. But later on when we're doing harder algebra, where there is some serious simplification required to get to that point where we can isolate x, then we are going to probably want to think about it this way. So here all we do is just combine x's, subtract x from both sides, right? And get, I'm not teaching you anything you don't know here already. We get 2x. There's my equal sign. Now if I'm going to be isolating x on the left, what do I probably want to do with the variables? Okay, good. I want to push them to the right. And when I talk about algebra kind of visually like that, I think that's a really good way to do it. I really do. I think you always want to think about algebra when you're manipulating equations as pushing terms around and isolating things. And if you think about it that way, as sort of flowing around this equal sign, that helps you to become a really good mental algebra student. So what do we want to get the 2 over here then, don't we? We subtract 2 from both sides, and that's going to give us a -7. And then all I got to do is divide by 2 and I'm done, right? Piece of cake. Now that's the same idea that we've got over here, isn't it? This is just harder. One other thing, very, very minor detail, and I'm sure you're aware of this, but let me just make sure everybody's on the same page. Why is it, was it just by accident that we gathered the x terms on the left here? Why did we push the x terms to the left? What do you think? Yes, ma'am.
Because you want the x to be first in the answer.
True, I want the x to be first in the answer, but there might be some instances where I might want to push the x over to the right. Now, when I'm all done, when all is said and done, if I get some number equals x, of course I can always commute those and put the x on the left, and you're right. But there's a specific reason. Hunter, what do you think?
Move this on.
Okay, good. We always want to gather the variable when we're solving an equation on the side where we have the most to begin with, meaning we want to have a positive coefficient, right? And if I'm starting off with a 3x here and a 1x here, if I subtracted 3x from both sides, I'd end up with a negative 2x, which isn't the end of the world. It's still going to work. But why go through the hassle of dividing by a negative number and potentially risking making a little mental mistake there when it's easier and less confusing to divide by a positive, right? So always, in general, we just collect the variable on the side where it's going to have a positive coefficient. Okay, so moving forward, with this one, what would we have to do? Just talk us through it. Without actually executing the steps, what would we have to do to eventually solve for x? First, to simplify, what would we do? Combine like terms. Which side are we going to gather the x's on? The left side, because 2/3 is bigger than 2/5. But that's going to be a pain, isn't it? I mean, you guys can all do this. But 2/3 x minus 2/5 x, we got to get common denominators. It's not hard, but it's time consuming. I'd have to push the 1/4 over here, right? You can see that we're going to be battling these fractions the whole way through. Now, with a group, you're an advanced group. I don't probably have to demonstrate this to make my point. I think you can see that when I've got to subtract my 2/5 x, get some fractional number of x's on the left, right? I'm going to add 1/4 and get some fractional constant on the right, and then I'm going to have to, if I did that, I would end up with, see if you can do this in your head, how many x's would I have? 2/3 x minus 2/5 x would be what? See if you can do that in your head. This is good practice. What would it be? 10 minus. So it'd be, wait, no? Yeah, 4/15. Right? 4/15 x equals, and then I get 5/6 plus 1/4. I could make those into 12s, couldn't I? Right, common denominator. What would I get then? 10 plus 3, so what, 13 12s? Now, how would I, just the only reason I want to reinforce one other thing. How do I get the x by itself here? How do I isolate it? Good, good. Yeah. A lot of times people answer divide by 4/15, which is technically true, but we never divide by fractions. We always choose instead to multiply by the reciprocal. It's easier, right? So we'd multiply both sides by 15/4 and get an answer, right? That's a lot of fractional work there, though. Could we make this simpler? Yeah, we can. Does anybody know a trick? Anybody know a trick for more effectively dealing with these fractions? I think I heard something. An idea, anybody?
You say cross multiply.
Cross multiply? No, we can't really cross multiply here. Cross multiplying is a little different. Cross multiplying we will do, but cross multiplying is the kind of thing we do when we have two fractions that are equal to each other. And that's one way to get rid of fractions. But I have more than two fractions here, right? And so that's not going to work. Okay, there's a trick. Now, you got to be careful with this trick, though. This trick, I'm going to show you a trick called clearing the fractions. Clearing the fractions works when you're adding a bunch of fractions, adding and or subtracting a bunch of fractions. When you've got multiplication worked into the mix, you got to be really careful with it. And if we have time today, well, maybe I don't want to take too much time on this today. I'll throw another one of these at you, just as kind of a warm up, where there is some multiplication involved, and then we'll talk about how we can deal with it. But for now, if we've got a problem like this, a linear equation involving a bunch of fractions, how do we deal with it? Well, you ask yourself, if I look at all the denominators, what is the least common multiple of all the denominators in the equation? Both sides. In other words, what's the least common denominator of all those denominators?
30.
30. Let's check it out. 6 goes into 30. Good. 5 goes into 30. Does 4 go into 30?
Oh.
60 would work, wouldn't it? Okay. 40 wouldn't work because 6 and 3 won't go into that, will they? So it'd have to be 60, wouldn't it? Now, if you get one that's too big, it's not the end of the world. It's just more convenient to get the smallest, the least common denominator. Any common denominator would work, but 60 in this case is the least common denominator. Okay? So once you find what the least common denominator is, we are going to distribute that through both sides of the equation. Now watch what happens here. If I distribute that 60 through, what's going to happen in each case to the denominator? Give you an example. When I distribute it to the first term, I'd get 60 over 1 times 2/3 x. Now when I'm multiplying fractions, of course we multiply fractions straight across, don't we? Right? But in many cases when we're multiplying fractions, if I multiply straight across, this is a pretty easy one. But I get a really big numerator and not such a big denominator this time. But we'd rather not deal with an enormous fraction and have to reduce that fraction. It's always better when you're multiplying fractions if you can reduce as you go, right? So here's where we could do some cross-canceling. 2 over 3 doesn't reduce on its own and 60 over 1 doesn't, but 60 over 3 does reduce, doesn't it? What's that reduced to? 20 over 1, okay? Now look how much easier that is, right? Now when I multiply straight across, for that first term I would just get 40 over 1, so just plain old 40x, right? Is that a surprise to you that the denominator disappeared? Shouldn't be. Shouldn't be, because didn't we pick specifically the number 60 because it's a multiple of all the denominators?
Yes.
Right? So 60 is a special number that's going to do, we handpicked, so it would do precisely that. It would cancel all the denominators out, right? So watch how you can do this. There's a way you can do this work, and this is part of the art of algebra, is not just knowing how to do the algebra, but to be really good at it, you also want to know how to abbreviate all the work in the notation, so you can do things efficiently and quickly. Look, watch this. This is a great way to do it. I need to do one thing. I got to move this down a little bit. Now watch this. Okay, 60 over 3 I know is going to reduce. What is 60 over 3? I'll cover them up. What is that? 20. So 20 is what's going to get multiplied by the numerator. 40, right? So that gives me my 40x. What's 60 divided by 4?
Negative 15.
Well, 60 over 4 is just 15, right? So 60 over 4 is 15 times my numerator. 15. Isn't that cool? Equals 60 over 5 is 12 times my numerator, right? 60 over 6 is times 5 plus 50. Now that's easy, right? From there on out, it's a piece of cake. Now I've got integers to work with. I can combine them easily. I can do my algebra without having to mess around with fractions. Yes, sir.
You're dividing the 6 and the 6 and the very last one, you're dividing the 6 by the 60 and then timing by 5?
Yeah.
Okay.
Yeah, you always, when you're clearing the fractions, when you distribute this big multiple, you can always reduce first, right? Guaranteed. So you always do that. What is this big multiple divided by 6? Well, 10. So that's what's getting multiplied by the numerator. Make sense? Okay, and from there we won't even bother. From there it'd be a piece of cake for you. Okay? Yes, sir.
What about the multiplication that you said? You said there was a hitch in multiplication. Were you going to show that?
Well, I'm not going to do it today.
Okay.
Yeah, we will. There is a hitch. When you multiply, just for now, the rule is, what if I had had something like, instead of just 2/3 x minus 1/4, what if I had had that times the quantity 1/2 or something? What you want to do is you want to go ahead and distribute that fraction through, which isn't a big deal. Multiplying fractions is easy. Just multiply that straight across, right? And I would want to get a sum, distribute the 1/2, and get new fractions that are being added, and then do this trick. But we'll do an example of that later. for today, this is really all I want to show you. Yes, sir.
I finished the problem and it ends up to be 65 over 16. So did you make that a mixed number?
Good question. Good question. No, you don't. In general, mixed numbers are for elementary school. We don't want to deal with mixed numbers. We want to just leave things as improper fractions. Okay, it's a better way to do it. You can if you want to. If you want to look at the relative scale of something, you can always make it into a mixed number. Real quick, because there are some mixed numbers on the assignment, here's another quick little deal. It's pretty easy to go from an improper fraction to a mixed number. For example, if I had like 29 thirds, how would I turn that into a mixed number?
How many times?
Good. Okay, good. Yeah, 3 goes into 29. How many times evenly? 9 times. With how many left over? 2. Right, so that's easy to do. Okay. How do we do the reverse? What if I have something like 7 and 5/8? How do I turn that into an improper fraction? Okay, good. So 7 times 8
Plus 5.
plus 5. 7 times 8 is 56. So 7 by itself would be 56/8 plus 5. So you just multiply the integer times the denominator plus the numerator. So 56 plus, what do we say? So 61, 56 plus 5, 61 eighths. Right? No big deal. And you all knew that, I'm sure. Okay, so new stuff for today. What I want to show you today, I want to push forward. I got the new assignment up and ready to go. I added another one that deals with just solving compound inequalities like we talked about yesterday. It's pretty short. I think it's 10 problems. Should be no big deal for you. What I want to look at today is solving absolute value equations and inequalities. Okay, this is it's going to be not a big deal for you, but I want to make sure that you're aware of one really important concept here. Okay, so the way we want to think about this, whenever you're faced with an absolute value equation or inequality, we'll start with equations. Say something like this: the absolute value of 2x plus 3 equals 11. Okay. Algebra is difficult to do with absolute value symbols. The algebra changes a little bit. It's more specific. And although, we're not going to do a ton of it this year, you will do more of that in the future. And you got to be a little careful with it. You really do. It's always advisable, and it makes things easier if we can trade an absolute value equation for one or more equations that don't use absolute values, where we can eliminate those, so we can do normal algebra. So you just kind of see the motivation for us here, why we want to do this. Here's how that works. Now think what an absolute value function really does. What is the job of an absolute value function? When I put inputs in, I input numbers into this function, what's it going to do to spit out outputs? For example, what's the absolute value of 7? 7. What's the absolute value of negative 11? What's the absolute value of 0? 0. Okay? So now think what it's doing. If you're the little man controlling the absolute value function, what are you doing?
Doesn't it show how far away from 0 it is?
Okay, it does show how far away from 0 it is. That's one way to look at it, absolutely. In terms of the outputs, what does it do? Okay, it's gonna turn negatives positive and leave positives alone, essentially, right? And leave 0 alone. It'll turn non-positives into positives. So, what are the possible values then of the expression 2x plus 3? If the absolute value is going to spit out an answer of 11, what values could 2x plus 3 actually have? Let me make sure, oh, by the way, when we're in here, I want to make sure all, like iPods and all those things, they have to be away, please. So what could it be? 2x plus 3 could equal...
Could equal a negative.
Okay, could equal negative 11. Couldn't it? Because the absolute value is going to make that positive. Or it could just equal positive 11. And then the absolute value would leave it alone. Both of those would be possible instances, wouldn't they? So we have to account for both of those. So whenever you see an absolute value equation, the absolute value of some argument, and that's the terminology we use in algebra. We say whatever's inside the absolute value bars is called the argument of that absolute value. The absolute value of some argument equals a constant. Well, then we have to rewrite that using an OR statement because there's two possible outcomes. Either the argument was already positive, or it's negative and the absolute value is making it positive, right? We have to account for both of those because those are both viable solutions. So we solve them both separately. Now, the steps are going to be the same, just different answers. What do I do in both cases to isolate x? First I subtract 3, then I divide by 2. Okay, and we can do that in our head. If I subtract 3 from 11, I get divided by 2, 4. So I get x equals 4. Or, what about over here? If I subtract 3 divided by 2. Okay, makes sense? Okay. Those both would work, wouldn't they? And I could plug those in and check. If I put 4 in here, I get 2 times 4 is 8 plus 3 is 11. Bingo. If I put negative 7 in, I get negative 14 plus 3 is negative 11. Absolute value of negative 11. It works, right? So that's one thing we got to do. Now, what about what if we do? What if we're dealing with an inequality? How about something like this? What if we have the absolute value of, we'll use the same thing. How about 2x? What do I have? 2x plus 3?
Yeah.
Is less than 11. Now think about that. That means that if the argument, if something is less than 11, let's even forget about the fact that it's an absolute value. If it's less than 11, 11 wouldn't work, but 10.99999 would, right? Make sense? So would, 10 or 9 or 8, all the way down. Make sense? So if the absolute value is going to be less than 11, then clearly a number like 10.999 would work. 10 would work, 9 would work, 8 would work, 7, 6, 5, 4, 3, 2, 1, 0 would work. Would negative 1 work? Yeah, it would, because I'm making it positive, right? Negative 2, negative 3 would be okay, negative 4, yeah, negative 5, 6, 7, negative 8, negative 9, negative 10. Would negative 11 work? Wouldn't, but negative 10.9999999 would, wouldn't it? Right? So really what we want to include then is all values that are trapped between negative 11 and positive 11, correct? Okay, so then here's what we do. When we see an absolute value of some argument is less than a number, we're going to trade that for the compound and inequality. It looks like this. The argument 2x plus 3 has to be trapped between negative 11 and positive 11. Make sense? Right? And then all we do here is solve that. So what are the two steps we go through here to isolate x? Subtract 3 from all three parts, and then divide by 2, right? And so we'd end up with, over here we ended up with a negative 7 when we did that, right? Here we got an x, and here we got what did we get, a 4? So that's my answer. Make sense? Okay? So what do you think's going to happen then if I do the same kind of thing, only this time the absolute value of 2x plus 3 is, let's say, greater than or equal to 11. Now we want values
At 11.
that are going to be, in a positive or negative sense, more than 11, right? So, for example, would 11 works in this case, but does 10.99999? Nope, it doesn't. 11.0001 does. Does 12, 13, 14? Sure, those all work, don't they? 9, 8, 7, 6, none of those work. Negative 8, no good. Negative 9, no good. Negative 10, negative 10.999, no good. Negative 11? That would work, wouldn't it? Negative 11, because the absolute value of negative 11 would make it a positive 11. So that one's okay. Negative 12? For my argument in here, would that be okay? Would the absolute value of negative 12 be greater than or equal to 11? It would, wouldn't it? Make sense? Okay, so then in this case, whatever's in the argument needs to be more extreme than positive 11 or negative 11, doesn't it? How am I going to say that? Did I? This one up here, oh, never mind. Okay. How am I going to say that? So the argument, 2x plus 3, is what? It's more extreme than positive or negative 11.
So is it a or statement?
It's going to be an or statement, isn't it? Yeah.
Disjunctive.
It's going to be a disjunctive inequality. So see if you can set that up. 2x plus 3 is, okay, greater than or equal to 11 would work, right? If this, whatever's in the green bubble is really big and positive, yeah, that's going to work. Then it's going to be bigger than 11, isn't it? Or, what else could happen? Yeah, it could be really big and negative too. Less than or equal to negative 11. And all I do is just solve those independent, right? Make sense? Okay. Got it. That's it. We're done with chapter 1. I think. Is there more? Maybe there's piecewise functions. Can't remember. But we're not going to do that today. Oh, no, I think that is it. Huh, it is. Not that I really care what chapter it's in, that's no big deal. Okay,